a uniform horizontal beam OX, 4.0 meters long and weighing 100 newtons is hinged at a wall at point O. It is supported by a cord XY, which is attached to the wall at Y. So there's Y, there's X, there's the beam OX. At 2 meters away from point O, I could think all 100 newtons, the weight, okay, of my 4-meter long horizontal beam can be thought to act right there in the center. Why? Because it's uniform, right? Uniform means the center of gravity is at the midpoint. So this is creating a clockwise moment. There is a clockwise moment from the weight equal to 100 newtons times 2 meters, or 200 Newton meters of clockwise moment. The cord here has a tension force in it, and the vertical component of tension acting right here is the thing that balances out this clockwise moment due to the weight, right? So we need an anti-clockwise moment equal to this from this component of tension. The actual tension in the cord is acting this way, right? Like there's a vector here and there's tension in this cord. It's attached to the wall. But some of that tension is doing what? It's just pushing it into the wall, right? Like there's going to be a force, or like this beam is being pushed into the wall by a horizontal component of tension that goes like that. The vertical component of this tension is the one that's providing the moment. Okay, because remember, only the perpendicular component contributes to moment. All right, so it's going to be the sine, so we can call this, force here T for tension, right? What is the tension in the cord? And we could say, well, that's going to equal the sine, right? Because it's opposite this 30-degree angle. In other words, I can work with this sort of vector right here, because that's opposite this 30-degree angle. That's the component of this tension that acts up, opposite 30 degrees. But when you draw it over here, it's hard to remember, oh yeah, it's acting 4 meters away, all 4 meters away, which is why some students would prefer to work with this 60-degree angle and say, well, it's adjacent to my 60-degree angle then. And so I could calculate it as the sine of 30 degrees times T, right? That component of tension is the one that's providing all of this anti-clockwise moment 4 meters away, or I could have said the cosine of 60 degrees T times 4 meters. Same thing. The benefit of working with the 60-degree angle is that you can really see visually, oh, that's where it's acting, right? This one you have to say, well, it's equal to the sine of 30, and I translate that opposite sort of side over here to remember, oh yeah, it's still acting 4 meters away. It's a mathematical artifact of working with this triangle that it's over here. Just because we draw it over here does not mean that that component of tension is acting on the wall, okay? It's just an artifact of how we draw the triangle. So draw, translate it in space, or draw this triangle, right? And consider the 90 minus theta angle. If I take my 200 Newton meters and I divide that by 4 meters, then I've got 50 newtons. So 50 newtons equals sine 30t. And so if I divide 50 by the sine of 30, which is a half, I get T equals 100 newtons. So I have a 100 Newton force acting 2 meters away, providing this moment. The entire tension in this cord is 100 newtons, but only 50 of those newtons are contributing to the anti-clockwise moment, right? So remember, we're solving for T, the entire tension in the cord. It's equal to the weight of this thing. But only 50 newtons of it, only the sine of 30 degrees, which is a half, times the 100, is providing the moment. Okay, so the other 50 newtons is like acting into the wall, right? It's pulling the beam into the wall, right? It's acting horizontally. And so just think about it. What did I just say this component was? I said it's 50. Is it very clear to everybody that 100 newtons acting 2 meters away is going to be equal to 50 newtons acting all 4 meters away? right? It's kind of like, okay, 100 times 2, that's my 200. 50 times 4, that's my 200. 200 newton meters equals 200 newton meters. Okay, so this does not solve for the component that's acting up. It solves for the actual tension in the cord. The component acting up was half of it, 50, right? Sine 30 times this. So the correct answer is D, 100. Not 50, right? It doesn't say what's the X component or the Y component. It says what's the actual tension in the cord. All right.